Check 1, check 2. Alright, just starting a stream here, getting the stream verified online as well as checking for audio. Where did it go? There probably is, but I don't quite know yet if there's a feature that tells you. I'd love to know if I could just look without having to open up the page if audio is actually coming through. But as far as I can tell, you pretty much just have to find your video and then turn it on to test. I'm paranoid now since I created a whole video without any audio at one point. So I like to double check and make sure. Before I get too far in. Okay, so we've got the live stream. Is it with audio? All right, and it is. So we can close that out and all these windows, as Elgato needs as much resources as possible, or OBS I should say. And I still haven't done color correction, so I'm going to try that after this video. But I started to do this, I wasn't going to record it, and then just to have something a little different, because it's a fairly standard repair, but I try to avoid it as much as possible just because it's time consuming. And this being even more time consuming than a regular BGA rework. So when we talk about BGAs and metallically bonded, this is what we're talking about. So ball grid array is what BGA stands for, and that's what these are. These are spherical solder balls. And you can see I'm not wearing any gloves, but I'm also not really interacting with paste. And why I said this is more tedious than normal is because normally we have a stencil and a reball jig that helps to kind of expedite this process. However, these are 0.35 millimeter pitch. They're tinier than most. And I don't have a stencil that is appropriate for this. So I've went ahead and ordered some. They don't really make them in the exact size format I would like to see, so I've ordered universals, which basically means they're going to have a larger grid area than what this actually requires, so you'll end up taping off the excess that's not needed so that you don't have balls falling through the unused slots of that stencil. And this is just a very slow, meticulous, time-consuming process. We do have flux thinly spread across this chip. And we're going to hope that when we heat it up, the chip doesn't move because it is so small that it will likely want to blow away. So we will use low airflow. We're going to stage our heat and try to get everything to stay the way that it should. And these balls will fly away. I actually have like a little dab of flux over on the left side, which, as you may be able to tell, no, you probably really can't. but I just dabbed the tip of these soldering tweezers into that, which gives me some stick to the solder balls. But it looks like there's a little bit of cotton from when I was using a swab that picked up some of that. So we had to wipe that off, because as you can see, it was picking up multiples, because that little strand of cotton was all it took to be able to lift several of these rather than just one at a time, which is what we want. And eventually you get into a groove and it speeds up a little bit, and then you get out of your groove and it slows back down. Got a little bit of shake to my hands, but I've learned how to kind of lock my wrist onto the table to try to help stabilize. And as you can see, I'm gripping lower on the tweezers to get, oh crap. I normally will take two hands and hold it apart so that I don't do what I just did, and that is let the other side of the tweezers kick solder balls that have already been situated. And we definitely don't want that to happen. And I have had days where I've made mistakes and wasn't paying attention. Like I said, it's so monotonous to manually apply all of these that eventually you just go kind of brain numb. And I don't know what exactly I was thinking, but I let my finger just kind of slide and knocked out pretty much like half of the balls I had lined up. At that point, I was ready to just take the table and flip it. But after taking a moment to cool down, I kind of got my wits back about me and started over again. Cleaning up some of this pad, just get some of the dust out of the way. It quickly accumulates. Like I said, if you get any debris stuck to that end of your tweezers, it's going to grab more solder balls than you want it to. So every now and then you got to just wipe your tips down, clean your area, whatever it takes to get it where you're just grabbing one. And it's best if you can get it just barely stuck to the tip of your tweezers, so that when it contacts that flux that is on the chip, that it has enough force to pull against what's adhering it to the tip of your tweezers. And this is tacky flux, which is why it kind of has this ability to grab even on such a small surface area. There are some fluxes out there that you could try doing this with that it just probably wouldn't work. So I would definitely recommend a tacky flux for manual application and really just BGA work in general, because you want those balls, once they're on their pads, to not move. And that's where that thin layer really comes into play. It took me a while to learn what was too much and what was too little. There's not a measurement I could quote, just because, I mean, we're talking about micron layers, and I don't know if it's, I mean, you can kind of see that gooey residue around the balls. There was also a few pads I had to rework on this one, so you're probably seeing some of that in the camera. You can see what I mean there by you want it to stick when you tap it and not stay stuck to the tweezers. And eventually that happens. It's basically you've gotten too much flux has built up around that tip, and at that point you probably just want to wipe it off with some type of a wipe. As I've said before, I use Kim wipes. and they're just basically a lint-free cloth. Their lint-freeness is subjective. I guess to a certain extent they're lint-free, but eventually they break down like anything else, and I find that I can still get lint from those. But I think it's pretty much a standard that most lab environments are using chem wipes. And even though it's monotonous, it eventually gets there. We've got 3 more rows remaining. Now, if this was a more complicated chip, I would just outright refuse to do it until a stencil was able to be shipped in. And I'll show you what I mean by more complicated for those that aren't familiar with ball grid arrays. I think I've got a old PS4 chip that I just kind of use as a point of reference for myself if I want to do probing or testing to try to discover any new intricacies of that chip that have been undisclosed by Sony or AMD, because neither of them are really going to tell you anything about them. And it's also probably about time for me to go ahead and start pre-ordering my PS4 Pro stencil, because the array, and that's the pattern that these are laid out in, is different from all the models before it. So up until the Pro, they all had the same array of these little pads that the balls go on for the PS4 chipset. And I certainly would not do an entire PS4 APU manually by hand. There's just way too many points of contact. The amount of time that it takes, you would just never turn a profit doing that. And there are people out there that do it that way, but those are typically in countries where getting a stencil is very hard, and the cost of labor per hour is low enough that it works out. Alright, so down to the last couple of pads. And then our next step will be to clear these excess solder balls out of the area. And then we're going to check that chip and make sure that all the balls are still aligned at least as well as they need to be. I mean, it doesn't have to be perfect. Nothing in life does. But it needs to be to the point where they're not going to be likely to slide out of alignment and end up bridging between each other. And if they do, we can fix that. It'll probably happen to 1 or 2 unless we get lucky. And if I get really unlucky, this chip will move on me. And I guess I could have mounted it into at least the chip, what would you call that without, I mean, it's the reballing jig, but you're just attaching it to the base without putting the top on because you're not going to use the stencil. So kind of like a chip vise. That would be a good way to put it. Just like a woodwork or a shop owner would use a vise in their job, we use a vise in ours, and it's specifically for holding that chip steady while we kind of do work on it. Whether that work is cleaning, reballing, inspecting, whatever it may be, you just want to kind of secure it. And that probably would have been smart of me, but I often like to do dumb things. So I usually tend to just throw it down on the pad and hope for the best. All right, so I'm going to go ahead and let's see. I'm already kind of zoomed in with the digital zoom, but I'm going to try to get us a little bit closer. There we go. All right, so really all we need to make sure is that we have a spatial gap between all of them. And if we had too much flux, where we had puddles, and there are a few areas that have a little puddle, but not so much that I think it's going to be a problem that when it heats up, that puddle will kind of boil it a little bit. And something about solder and flux, when it gets hot, it likes to attract itself. I think somebody described it very well, where the heat only makes it more so, and that's probably got something to do with, as those molecules become excited, they start to want to kind of run around. But like metals, they described it as, and what's the guy's name, because he has a channel, The Art of Repair, but he described it as like metals want to come together. And that's a very good description, because if you end up seeing any of these bridge, you will literally watch them try to pull themselves towards each other rather than to the pads. And even though they're a like metal, the difference is that heat is more readily accessible to the solder joint or solder balls than it is to the pads underneath. There's a bit of heat sinking, which we talk about a lot, or at least I talk about a lot, and I think plenty of other YouTubers for the repair industry do as well, is that the thermal loss, and that's a good way to put it, is that occurs between the solder ball itself and the pads underneath with all the material surrounding them. The pads have a far greater thermal loss, and they take a longer time to ramp up because they're losing that heat. Whereas the solder balls, until they join, are not going to lose their heat as rapidly because they're just kind of resting on a suspension of flux right there. All right, so I think we've got most of these in a good alignment. Like I said, it doesn't need to be perfect. We just want to make sure that they're sitting on their pads and that they're not ready to ride off and go join forces with another one. And you see how I talked about this earlier, where I grab the two ends of the tweezers, and this also helps make my hands a little more steady. I don't know if in the video it shows, but this is a pad that it was part of the problem with this one was it was so badly oxidized that the pads were no longer able to really send their signals, causing drift issues and a bunch of unresponsiveness issues and just random strange button presses. And that was related to the signal being blocked due to corroded pads that just had oxidized past the point of really being usable. And so I had to clean this off and then scrape away that oxidization, and it was so bad on one of those that it required a little bit more work than what I would have liked it to, and it caused it to almost bridge between these two. But that's where we took something that I've used before and talked about, which is called the mask, which is that green coating that the manufacturer puts on there. But we applied a liquid mask, and you can see that shade of green right in this area is slightly lighter. Is slightly lighter and brighter than the rest of it. And it is a thinner layer, but it's good enough that it's going to prevent it from bridging those two contacts and causing it to basically fail. All right, so at this stage, we're going to go ahead and get our airflow. We're going to start out with a low heat and a low airflow amount. We just kind of want to warm it, get everything to the same temperature. And then we'll bring that heat up slowly. And once those solder balls have started to kind of melt and join just a little bit to give them some grab, at that stage then we can turn the airflow up because we don't have to worry about blowing the solder balls completely off of this chip. And when we do turn that airflow up, we're going to make sure that we have the chip held in place somewhat. And in fact, we can already see where two of these have tried to join together right here. And my rule is if you can't get them to come apart, if you can't get them to stop from coming together, so either it's fighting you, which probably means there's too much flux there, or if it keeps wanting to return back to the path, then there's enough of flux down underneath them that it's going to kind of ride that like a wave until they join forces again. And at that point, you're just going to make more work for yourself. So the easiest thing to do is just go ahead and remove one of those balls and then let the other sit on the pad that it's most likely to gravitate towards. And then this one is not sitting on its pad. And now we can turn this temp up. We're going to go to about halfway. And at this point, just so we don't overheat any particular area, we're going to go ahead and start moving that around. When we were at a low temp, it wasn't as necessary. And I'm not going to get into exact temps just because, again, your own skill as well as the device you're using is going to kind of dictate how you need to stage these profile attempts. So I think it's better to give that starting out with low temp, using half or 3/4, and then let you make your references from that based on your own experience. All right, and then we're going to go to our 3/4 temp. And you can see probably some of these balls look a little dull, other ones look a little more shiny. So we're almost at that melting stage where they'll start, in fact, I'm starting to see balls that are bonding. And we're going to go ahead and go all the way up on temp. And we're going to increase our airflow a little bit. And again, we keep it moving so that we don't overheat any one area. And then I think at that point we are good. All right, so we did have some move, but we didn't have any that had an issue. We didn't lose the chip, so we got lucky today. I didn't make any mistakes. Yeah, that shows everything. And then now what we're going to do is go through and clean this up, and it will be ready to install onto the board after that. All I probably shouldn't have done that with bare hands, but oh well. Alright, so at this point I normally would go ahead and put gloves on, but we're already almost done because I will start touching the chip at this stage normally, but as long as I can keep my tweezers only as our contact medium, shouldn't need to do it. And I'm not sure if you can see, but after rubbing it with the cotton swab, you're going to get cotton fibers that are on that chip. So I use the cotton swab to kind of clean off the flux, and then as my last step, I use the horsehair brush to kind of do the more detailed clean, which will also help to get a Kim wipe. Got a rogue horsehair there. Because again, I'm sure you can probably tell this looks like it's been cut. These aren't all even. And that's because when I buy these, they're about 3 times this length. And I just find they're not stiff enough to really get in between those balls and clean them up the way that they should. Sounds weird saying that out loud. Sometimes you have to turn this into the light, like put it on its side, which will allow me, and that's what I was doing there, is I can see other straggle of pieces that are lingering by just basically changing the light. So I want to get as much of that out as possible. We don't want to have any of this debris on there. It may interfere with our electrical connection. Now, at a certain point, very teeny tiny pieces aren't going to cause us issues. So it can get nitpicky here, and you'll see some people that really don't even bother going into detail with cleaning them, but I feel that it's important to. Now, I don't do this on most controllers. If this was a standard controller, it's not profitable to do this type of repair. This is on a Xbox One Elite controller. This is something somebody paid $150 for. So rather than going and spending another $150 to get a replacement, they can spend a little less and get it fixed. All right. So we're cleaned up. And I'm just disconnecting the board here so that I'm not having to work around everything else that it was connected to. It's got its kind of power lines and sensor lines soldered, and there's a two-part board to this, so that's where disconnecting the secondary part. Also, if you are going to work on the IC, you're going to need to remove, but you can see this has already had replacements put on. Previously, I'd replaced these as well as done a reflow on the IC, thinking that would do the trick. It did not do the trick, so we're having to replace it. And in order, well, reball it and reinstall it. In order to remove this without damaging the joystick, you'll want to remove it. If you don't remove it, you're going to end up overheating it, and it could either warp or you're going to melt what little bit of lubricant it uses on the gearing. But I think even more so than that, before that even starts to kind of get liquid and slide out, you're going to find that you've probably, at least to some extent, warped the standoff that it uses to kind of pivot on its axes, or axes, however that is pronounced in plural form. And then once that takes place, it won't probably kill your gameplay, but it might seem a little odd. There might be movements, or maybe the return of the joystick won't be exactly the way you remember. So don't be lazy is the main thing learned from that, is take the extra time, remove it, and then reinstall it after you're done with the IC. And I was originally planning to stop it after reballing the chip, but I've decided to move forward. So at this point, I should really quit BSing and put gloves on. Now, it would probably be better to replace this chip than to repair it, but getting these, in fact, let's just go ahead and check. I think I've checked this before and found that getting a replacement is impossible, but let's check it again and see if that's changed. So basically, the only way to replace them is to pull it from a known good working board that may either have other issues or that you just want to use as a donor board and you swap it out. That would probably be the easier route if everything on that board is functional. MKL26. C256VMC. Now, when you're doing this, manufacturers like to take these chips and rebrand them. So I did notice that there's a MKL26Z64VFT4. Is that what I just typed in? No, that is a chip that already exists. And what we want to look at on this, and I know you can't see my browser window, but I want to look and see if this chip appears to be exactly the same. No, it does not. So this is definitely a proprietary IC as far as I can tell. For the Xbox Elite controller, you're going to have to either pull this chip from somewhere or you're going to just replace this board in its entirety once we get to this stage. All right. And again, this shows where at least this part is made easy for us, which I already knew the orientation of where it went. But you got a dot here. Oh, you couldn't see that. You got a dot here on the board, and you've got a dot on this chip right in that top left corner, which means that this is the orientation you want to have your chip situated in. And we're going to try to keep it in that square as much as possible. But before we throw it down, put a little dot of some flux there, and then we're just going to spread that flux. Now that's spread evenly over that area. I like to come back with a Q-tip and remove the excess from the edges, because if you remember, I said that those solder balls will just kind of ride on top of that flux once it gets heated up. So if you scrape some of this excess away or wipe some of this excess away, you can help to prevent that from kind of moving in a direction that you would not like it to. All right, and so for this, we're going to rely less on the microscope camera and more on that background camera where you're just going to kind of get the general flow of what's going on. I will let you see again the alignment. And now that we have the flux on there, it again, tacky flux, it should kind of want to hold itself a little more in place than it did when I just kind of threw it down on there. And in fact, you can see that it hasn't gone anywhere yet. So it is slightly adhered to the board, but if you start tapping and flicking or you blow too much air too fast up underneath it, it will just blow away. Is basically what will happen. All right, and I'm just trying to check the alignment, but looking at it through the microscope is a little bit difficult. Probably would have been easier if I'd have removed that other analog leg, but I'm not going to. We're not going to get heat that far that side over. So what we're going to do is now turn our temp back down, turn our airflow back down. Now I use my finger as kind of a temperature sensor as well as a block. You can see my left hand, I've got my finger over that plastic piece, and that's just so that it doesn't get airflow. We could just tape that off. That would be one way to go about it, but right now we're just doing kind of like a low heat warm up, bringing the board to temperature. And this part, it's better to go slow than to try to speed it up with more airflow. You get anxious and want to be done with it quickly, and you're going to end up causing more work for yourself. These are words spoken from experience. When you're trying to earn a living doing this, you want to get it done as quickly as possible. but rushing through it will only make life worse. And this is probably the most critical step, is getting this board. Like I said, these gaming system boards are made so thick, so much thicker than cell phones, that getting that board kind of pre-soaked with heat is that first step and the most critical step. You want to make sure there's enough heat throughout the board's surrounding area that it's not going to start rapidly dissipating heat as you turn it up. But we are ready to go to our next temp. And we're going to go to that halfway mark. And where we get a good sense of what's going on with the board overall is we can start to see the chips that are around this one. Their solder is exposed. We can see what's happening on it. Now, if I had my my more side flex twisty mounted camera mount back from the machine shop, I would be able to actually then point this camera in a direction that would look down at an angle to those balls underneath and be able to know exactly when they were starting to melt. And so that will be coming here shortly. But I got this stand from the manufacturer because I wanted to be able to use it for that purpose. But the way that they threaded it was just wrong. Well, I won't say it was wrong. It works. It just works half-assed. If you aren't paying attention, the threads will back off themselves and the stand will become loose and you will slam your camera into the table. So I have a machine shop putting additional threads on it so that it can be locked in place and I no longer have to worry about it breaking cameras. All right, we're going to turn temp up again. We're at about 90%. And now we're going to crank airflow up a little. Now this is the quick station, so my airflow goes up to 100 at this temp because I'm over 400 degrees. So I'm currently at about 36 on airflow, which means that's about, well, 36% out of 100. So again, still not using huge amounts of airflow, but enough of it so that I can pressurize that hot air enough to get it to flow up under those inner joints, because we need the entire area to get wet. And what we mean when we say wet, I don't know if you can see these chips on the right hand side here and are much more shiny than the ones on the left, and that's what we call solder being wet. That's what we want to see. I was using the microscope for my purposes. You're using that back camera, but I'm going to go ahead and back this up. You'll be able to see more through the microscope, as well as I be able to look down that inner edge and see where we're at in terms of the overall entire chip being soldered. And I think that is it. Let it cool a little bit, and then we're just going to do one more heat blast. Basically, I'm allowing that solder to kind of harden and rise, and then reheating to try to get it to set again, just to make sure all of those pads have adhered and that we're bonded all the way through with our solder balls. And I can tell already just from looking in there that some of those pads seated a little bit better. And again, this is where I'm telling you this stuff and you're like, I don't know what he's talking about if you've never done this before. But eventually you get a feel and an understanding for the medium that you're working with. And ball grid array, VGA repairs, it takes experience and it takes practice. The more comfortable you get with it, you start to look at these things and you go, oh, okay, I can see that one of these pads, in fact, one of these in here does look a little dull. Can't tell if that's really from underheat or maybe not enough flux on that particular ball, but I can still see that even though it's not what I would consider a perfectly joined solder ball, it's still efficiently enough metallically bonded. And I like to use that word because it iterates exactly what's happening. What's going on here is that we're metallically bonding this chip to this board. And we're doing that through our VGA spheres, which is the ball grid array pattern that we talked about earlier. So getting a little technical on everybody, kind of going in depth on detail, which is probably more than most of you care to hear about. But if you're trying to get the information you need to learn to do this on your own, trust me, eventually those words will click and you will say, oh, okay, I understand that now. But if you also want to look at VGA solder joints, there's plenty of companies out there that either sell the spheres or sell the equipment that have done mock-ups and like demonstrations of different types of joints and what they look like. Well, the different types of joints that are considered not good and good, and what problems cause those particular like dry, cracked, not properly heated enough, so the ball hasn't gotten wet enough to allow the chip to kind of drop under its own weight, which is a good indication that your chip is seated properly. So if you see any unlevelness to your chip, that's usually an indication that you didn't heat all sides. You got half of the chip maybe to its wetting stage, and the other half of the chip was never really fully heated. So some of those balls sunk under the pressure and the other ones are still standing up at their highest point, and your chip gets a little wobbly. And it may even work that way, but in all likelihood it would not work for long. Okay, so at this stage now I just have to reassemble, and if you're curious what this looks like, there's the base. This drops in. We're then going to attach these wires. Like I said, I haven't gotten the setup. I did realize that my problem is not with my switch. It is the issue with HDCP, that it actually, the Elgato does what it's supposed to do. It respects HDCP, which is content protection, so that you're not copying and recording either movies that are streaming or other things that are going on, and you have to turn that off. And turning that off on each person's machine until it's just right, it's a pain in the butt. So what I really need to do is set up a camera that just looks at the screen, and then I can switch to that view so that you can watch it. But like I said, this still has to be tested because this chip may be done for. And if it is, then I'm probably just going to go ahead and swap it out for a board that I have already fixed and repaired. And at that stage, if I get more of these chips in the future, I'll have this one marked and notated that this is the only problem with it. And when I get one that is good, something else is wrong with the board, I can then pull it and put it onto this chip. And at that stage, like I said, I've already ordered the stencil, so I would no longer have to manually reball this. Probably in this year alone, I've done that manual reballing Again, I don't get them often, so it's probably been done about 20 times, but I just finally got to the phase where I'm sick of it. I don't want to manually reball it anymore, so I ordered a stencil. If you're curious what those look like, go on eBay. There's plenty of people that have them listed. Quality of these stencils will vary, so it's buyer beware. Most of this stuff is made in China, and that is the Wild West for manufacturing. There are no standards, so however the person wants to make it. I've gotten some where, and if you're wondering what a stencil is, I've gotten some where they just don't have all of the holes properly, whether it was laser cut or CNC cut. You can see here, I think this one actually had some unevenness to it, so I would have to take the tweezers and kind of push on it, which is why you see these divots. I've actually bought replacements for these. I found that eventually I go through them, so I ended up buying about 10 of these, and these are just for the PlayStation 4 because that's probably the one that I reball the most. And like I said, now there's the PlayStation Pro uses a different configuration pattern. If you can see that pattern there. Sort of, kind of, well, good enough. But the PlayStation 4 Pro uses a different one, so now I need to order a set of stencils for that. And here's an actual PS4 chip. That may actually show up a little better, where this is the ball grid array where I talked about, and this is much more complex. I will never, ever, ever, ever in my life manually apply every single one of these solder balls. This would be ridiculous. It's just not going to happen. If you request a video from that, you'll probably get an emoji that looks like a middle finger. Way too much work. But like I said, if you want to see somebody manually do that, I'm pretty sure they either speed through it or they cut through it. But there are videos of people manually applying these balls. Now, when you, let's say I had reballed this, and it had these missing from these pads. Depending on how I felt that day, I would either just scrape it all together and re-stencil it, or I may go back in and individually just reball those areas that did not get an adherence. So I will manually do it that way. I just won't do all of them because I'm pretty sure, I haven't done an exact count, but I want to say it's close to 1,000, whereas the other one was 111. And you came in on the last 3/4 of that, and that took still quite a bit of time. So you can imagine how long it would take if you were doing the whole thing from scratch. But like I said, I'm not going to reassemble all of this as part of the video. I'm going to go ahead and put it back together probably later today. I've got a few other projects I need to finish up before I go in to start testing this. And it, like I said, will either pass or fail. If it fails, then I'm just going to swap this out with one from a good. And if it passes, I will actually be tickled by that fact because, really, to be in all honesty, I expect this chip to fail. There was so much oxidization on this pad that I don't think that it's possible that it survived, but it was great for making a video, and I'm going to try it just to see because, like I said, it's not a chip you can order. You can't buy it. You have to pull it from somewhere. So if it is possible to salvage the chip, it has a great potential for increasing the ability to do this job in the future, because I know that maybe the success rate of those chips, that even though they're badly oxidized, they are still more than likely good. And so you spend that bit of time, and this is where people wonder, why do companies bill flat rate? It's because, one, if we charged you by the hour, you would never want to pay it. Companies that do this type of work for military contractors, they're billing $250 an hour to do the exact same thing that I just did, but on a higher grade of equipment. They're working on equipment that may cost hundreds of thousands of dollars or millions of dollars. They're building cutting-edge equipment where maybe their only cost is manufacturing, but the amount of time that it took them to prototype and make that, who knows what the cost is in it. And they do have specialized equipment. They would not do this manually. They're going to do all of that by a very precise piece of reballing equipment. And I would love to have one of those, but I've seen a few that cost from hundreds of thousands on up. There is probably one I would like to get one day in the future that is about, was it like 35 to 50,000? I'm going to have a lot bigger increase in BGA work to justify that expense. But the biggest thing that I liked about it was almost fully automated. It would even glide across the surface of what you're working on and vacuum solder it. Now, it wouldn't for this, but for a standard board like a PS4 that uses kind of that standard die chip size, it would knock those out, and it would make the removal, preparation, and then replacement of that chip much more efficient. And the faster you can do it and do it precisely, the more jobs you can do. However, like I said, for this, billing flat rate is simply because you set an approximate value and you charge that, and in the jobs that take longer, you are eating that loss. In the jobs that go shorter, you're making that gain. And the idea is that in the middle, you average it out somewhere so that the burden is shared rather than individualized. And some people go, oh, I got this repair and it cost me $45. And another person goes, oh, I got that repair and it cost me $200, which no one would pay for a $150 controller. So that's a little bit behind why you would want to stage this out. But also, let's say this was the first time I had ever done it. The very first time I did this, I had to put all the research and development into what the problem and the solution was, which meant I had to actually figure out that this chip was the issue. And we did that first by replacing the joysticks. And we still had drift and other weird responsive issues from the controller. Like one of the problems with this was when you go to click on R3, you would actually get a fire action, which should have been R2. And other times you would click on R3 and it would cause your guy to crouch. So it was just very intermittent signals that just didn't make sense. Now I knew immediately from that then our IC was the problem, but the very first time I didn't. So then afterwards you go to inspect all of the chipsets around it. And you start looking for, are any of these knocked off? Have any of them failed? Is there a short? Is there an open? And you're just probing and testing. And then you start getting into, where do all these trace lines go? And how does it connect? And what goes to what and what goes to where? And I have also done in the past and still do for very specialized requests. They're not cheap, but I'll make custom modifications to controllers where they want to move buttons, change buttons. I don't really get into the cheats where they want to add in abilities that are programmatic that take away from the fairness of it. It wouldn't be to say that I would never do it, but if I knew it was somebody that wanted to try to, one, they ban those in competitions, but wanted to try to use it for aggravating purposes, I wouldn't contribute to that just because simply I can't stand it myself. So I'm not going to potentially arm a person to get online and be a pain in my butt. However, I have done things like moving the PS button on a controller because I myself find that my thumb slides off the joystick and then slaps that PS button, and I can't stand it. It drives me absolutely crazy, especially when you're in the middle of either a Fortnite battle or I like to play Monster Hunter, and next thing you know, you're looking at your main menu screen and you're still getting your butt kicked or killed. So just some of the things that I've done that have helped me to figure out what's going on here is basically tracing down all of those issues behind how does these signals work and where do they go, and what it all boils down to is that the signals are going to come through these joysticks, and at some point in stage they're running through this IC, and that IC then kind of either does something computational or, and I guess that is the brain. There are no other thought processes here on this. So, it's flipping high and low signals and doing something with them, redirecting them so that it can then go back out. In this case, because we now use mostly Bluetooth, it would be converting those signals over to whatever this Bluetooth needs it to be, or there may be a controller chip inside of here that does that conversion, but it's got to send that input-output from here to here, and then it then codes it for Bluetooth, which is then streamed wirelessly to our console. But if you're streaming over the USB connection, which is actually on the top on this is a different port. your USB connection is here. If you're connecting via USB and sending it, then again, all the signals are coming from this chip, but it now knows that you want to send the signal over USB, and it's going to redirect that signal through these little connectors on this side, back through to the connectors on, so I said the connector on, you can't see it, right here, through the connectors there, and then up and into whatever channels, through whatever vias we have going on here, through our USB and into our console. Outside of that, I mean, that's essentially this entire device on a nutshell. And you can see all of these small components. I mean, it's possible that sometimes these go bad. It's more probable that they get knocked off. So you want to check and make sure that nothing's missing there, nothing's damaged. But I haven't seen too often where these have gotten shorted out. I have seen it, but I haven't seen it enough for me to say it's usually your problem. 9 times out of 10, if replacing these doesn't work, you need to just go get a new controller. If it is a more valuable elite controller, scuff controller, whatever your provider calls it, then your issue then probably revolves around the chip. So if you're able to replace it, go for it. If not, then you want to get it fixed, you need to send it in to somebody. Other than that, that's enough ranting for today. Like I said, I've got other stuff to do, but I always like to try to share a little bit behind the what and the why. So if you have any questions, feel free to ask them in the live stream. I may do another one before the end of the day, but for now, that's it.